Hey everyone, in this chapter we're going to talk about quantum theory and atomic structure. So the first thing we need to talk about is light. Light is what allows us to see matter, and light is made up of subatomic particles that we call photons. Photons are approximately similar in size to those of electrons, so they're very, very small, and their behavior is quite similar in terms of how they travel and move. Quantum mechanics is the overall study of energy, nature, matter, of the subatomic world, and with particular interest in photons and electrons. And so we're going to take a little bit of a journey through history of quantum mechanics, as exciting as that sounds, where we found that initially, before modern quantum mechanics was founded, light was thought to only travel as a wave and matter traveled as particles. And I'll describe what that means a little bit later. But current quantum mechanics says that light and matter both have properties that are similar to both light and matter. So they both travel as particles, they both can travel as waves, they have what we call wave-particle duality. So let's talk a little bit about light and the properties of light. We know that light travels as a wave, and there's some important properties about waves that we're going to talk about in this chapter. The most important properties that we're going to talk about include frequency, wavelength, and energy. We'll also talk just a little bit about amplitude, but we'll focus on the other three. So first, the frequency of a wave, represented by the lowercase Greek letter nu, that's the wind-blown looking V symbol right here. That's the number of complete cycles of a wave in a second. And if you look up to this example wave up here, the height of one peak, or starting at the top of one peak, going to the next one, that represents one complete cycle. So in this example right here, we have 4 cycles in the timeline, which is 1 second. The units for frequency are seconds to the -1. Another way you could say that is inverse seconds. And that's exactly equal to a hertz, which is represented by capital H lowercase z. If just a little bit of an algebra review, 1s to the -1 is the same as saying 1 over seconds. So seconds are essentially in the denominator here. Wavelength is another important property about a wave that we'll look at. Wavelength is represented by this lowercase Greek letter lambda, and that's the distance between the successive peaks of a wave. So if you were to start at the top of this peak and measure the actual distance between the top of this peak and the top of the next peak, here to here, that would be the wavelength of the wave. The units for wavelength are any reasonable unit of distance, but the most common are meters, nanometers, and angstroms for really small waves. We've already talked a lot about energy in chapter 6, but we'll talk about the energy of the waves and how it relates to the wavelength and the frequency. Here are some comparisons of the important properties of a wave. We have wave A, wave B, and wave C. And you can see that wave A has the longest wavelength, so the distance between the successive peaks is the largest. It also has the lowest frequency. So if you count the number of cycles, there are 4 cycles. And because it has the lowest frequency, it also has the lowest energy. If we go down to wave C, we can see that these waves have the shortest wavelength, so the smallest distance between the successive peaks. And if you count the number of cycles in the same amount of time, this has the highest frequency. And so there are 16 cycles in the same amount of time. And because it has the highest frequency, it also has the highest energy. And then this is the extent where we'll talk about amplitude. The amplitude of a wave is the height of the wave. So from this central line here, the distance. The higher the amplitude is, the brighter the light is going to be, or the more intense the signal is going to be. The shorter the wave is from this middle peak here, the lower the amplitude and the dimmer the light, or the lower the signal will be. So now that we've talked a little bit about the relationships between wave properties, let's talk about them in a more mathematical sense. This little symbol right here means is proportional to. It sort of looks like an infinity symbol that has the tail cut off. And so if you see something like x is proportional to y, that represents a direct relationship. As x increases, so does y, and you'll see a positive slope if you plot the two variables against each other. If you see x is proportional to 1 over y, that represents an indirect relationship. As x increases, y will decrease, and vice versa. And you'll see a line with a negative slope associated with that. And so for those 3 wave properties, frequency is proportional to energy, which are both indirectly proportional to wavelength. What that means is the frequency and the wavelength are indirectly related. Something with a wave with a high frequency has a short wavelength, and a wave that has a low frequency has a long wavelength. Energy is also indirectly proportional to wavelength. A wave that has a short wavelength has a high energy, and a wave with low energy has a long wavelength. Frequency and energy are directly related to one another, and a wave that has a high frequency has a very high energy. A wave with a low frequency has a low energy. And so that brings us to the electromagnetic spectrum. Light is classified based on the wavelength of the waves, and then the frequency and the energy can be inferred if you know the wavelength because you know the relationships between those. And so we have several different types of light that including gamma rays, X-rays, ultraviolet rays, visible rays, which include the colors Roy G. Biv, infrared waves, microwaves, and radio waves. And the way this electromagnetic spectrum is organized is it has the shortest wavelength, highest energy, highest frequency waves on the left, the gamma rays. And here's an example of what those waves look like. You can see they're very close together, so short wavelength. There's many cycles in a short period of time, so that represents high frequency. And as we move from left to right, we get over to radio waves, which are the types of waves with the longest wavelength, the lowest frequency, and the lowest energy. You can see the distance between the successive peaks is very large for radio waves, and so you can't fit as many cycles in the same period of time, so they have a low frequency. And they also have low energy. And so this is the electromagnetic spectrum. There are many versions of it. This is the one I will stick to. So what do you need to know as far as testing goes? Well, you're not going to have to memorize the entire electromagnetic spectrum with respect to all of these values. That's a little ridiculous. But you will need to take one of these. If I give you a blank electromagnetic spectrum, you should be able to fill in the types of waves. And then I found a mnemonic device that I like. The only problem with the mnemonic device is that it goes in the opposite order of the electromagnetic spectrum presented. So you'll just have to remember to reverse it. So the mnemonic device is Raging Martians invaded Roy G. Biv using X-ray guns. And so R is for radio, M is for microwave, invaded for infrared. Roy G. Biv represents the colors red, orange, yellow, green, blue, indigo, violet. Using represents ultraviolet. X-ray, no secret there, that's X-ray. And then guns stands for gamma rays. So you should be familiar with the order that these go in, and that gamma rays have the shortest wavelength, highest frequency, and highest energy. Radio waves have the longest wavelength, lowest frequency, and lowest energy. And one thing to be aware of, you may see the term electromagnetic radiation. It's just asking you about what type of light. So electromagnetic radiation and light are often used interchangeably. Next, we'll talk about the speed of light. The speed of a wave is measured in distance per unit time, just like you would measure any other speed measurement. Though the speed of light is typically expressed in units of meters per second. And in a vacuum, a space that has no matter in it, all electromagnetic radiation, or light, moves at what we call the speed of light, and that's represented with a lowercase c. The speed of light is a constant value that we can use to convert between units of meters and seconds. And that's convenient because wavelength is usually expressed in meters and frequency is expressed in seconds to the -1. And so the speed of light helps us to relate the frequency and wavelength of light. If you know the frequency of a wave, then you can calculate the wavelength and vice versa. And the formula is C is equal to frequency times the wavelength. The important part of this equation that you'll need to remember is that the frequency is expressed in units of s to the -1 or inverse seconds, and wavelength has to be expressed in meters in order for this value to work. So let's do an example using the speed of light calculation. So if you have a red light, say in a barcode scanner that has a frequency of 4.62 times 10 to the 14, that's a very large number, inverse seconds, what is the wavelength of that light in nanometers? And so we can use the equation C is equal to frequency times wavelength because we know two of the variables. And so the first thing I would recommend that you do is to rearrange the C is equal to nu times lambda equation to solve for the variable you're looking for. In this case, we're trying to find lambda. And so if we divide by frequency on both sides, we get lambda is equal to c over nu. The value for c will be provided, and that's the speed of light, 3 times 10 to the 8th meters per second. And then we can plug in the value for frequency. And you can see here that the seconds are going to cancel out, and we'll be left with a value in meters. The value you should get is 6.49 times 10 to the negative 7 meters. Though the question specifically asks for the wavelength in nanometers. This is just a simple metric conversion, so if you remember your metric conversion for the prefix nano, you should be able to handle this. And so there are 1 times 10 to the 9 nanometers for every 1 meter. When you complete the calculation, you should get 6.49 nanometers. And you can use the electromagnetic spectrum to double check your answer. For instance, we have a red light, so we expect that the light will fall in the visible region, specifically the red part of the visible region of the electromagnetic spectrum. And if you look at the wavelength values on top here, values for red light are usually between about 600 and 750 nanometers. And so we get a value that's 649, which corresponds to red light. So we can be sure that that is the correct value. So now we have a way of relating the frequency and wavelength of a wave. And next we're going to look at how to relate the energy and frequency of a wave. Those two properties are related by what's called Planck's constant, which is represented by a lowercase h. It's the value that links the amount of energy a photon has with the frequency of the electromagnetic wave. H is equal to 6.626 times 10 to the negative 34 joules times seconds. So this is a very small number. And the equation for that is the change in energy is equal to Planck's constant times the frequency. And the important part of this equation that you'll need to remember is the units that each variable is expressed in. Frequency is going to be expressed in inverse seconds, and energy will be expressed in joules. So we've talked about two different ways to relate energy, frequency, and wavelength. We have the speed of light relating the frequency and the wavelength. We have the energy and the frequency related by Planck's constant. But what about the energy of the wave and the wavelength of the wave? They also have to be related. So you can actually derive an equation. Don't worry, I won't make you actually derive the equation. I will just provide it to you. But for those of you who are interested in where the equation comes from, if you take the speed of light equation and you solve for frequency, frequency is equal to speed of light divided by the wavelength. And if you take the Planck's constant equation and solve it for frequency, you end up with the energy divided by Planck's constant is equal to frequency. So what you can do, if frequency is equal to both of these, you can set them equal to each other, which is what I've done right here. And you can rearrange the equation to solve for one of the variables. Here, now I have an equation where I have the energy of the wave related to the wavelength of the wave, and you can see that they're related by Planck's constant. Again, you just have to remember what units each variable is expressed in. So let's do a couple of example problems where we practice using these equations and choosing the correct one. This is an ALEKS example. Don't be deterred by the large number of words in the question. It's actually a pretty straightforward question. I'm not going to read all of it to you, but the important parts of this question that you should be able to pick out is that we have radio waves that have a frequency of 1.7 times 10 to the 4 megahertz. Remember, a capital M is the metric prefix mega. And we want to calculate the wavelength of these radio waves and express the value in millimeters with two significant digits. So on the exam, you'll be provided a lot of equations, and you'll see something that looks like this box right here, where we have those equations we just talked about and the respective constants. What you're going to need to recall are the units that each of them are expressed in. And so what we're going to need to do is take frequency and convert it to wavelength. But we know with all of these equations, the frequency has to be expressed in inverse seconds, which is the same as hertz. So the first step for this problem would be to take the value we're given and do a metric conversion to hertz. And so we have 1.7 times 10 to the 4 megahertz. And if you remember, the prefix mega means 1 million. So there are 1 million, or 1 times 10 to the 6, hertz for every 1 megahertz, which means we have 1.7 times 10 to the 10 hertz. Now we can apply these wave equations to calculate the wavelength. And so you're going to have to be responsible for choosing the correct equation. You have frequency, you want wavelength, so you need to find the equation that relates those two. And that would be the speed of light equation. And so you have c is equal to frequency times wavelength. Again, I recommend that you rearrange the equation first to solve for the variable you're looking for. In this case, we want wavelength, so I will rearrange the equation to solve for lambda. Lambda is equal to c over v, and then you can plug in your values. We have 3 times 10 to the 8 meters per second, and we have our frequency expressed in hertz. I'm going to change the units over so it can become clear how your units are going to cancel out. Meters over seconds is the same as a meter times an inverse second. And remember, a hertz is the same as an inverse second. And so it should be clear here how the inverse seconds will cancel out and we'll be left with a value in meters. And so you should get a value of about 0.01765 meters. I have not rounded my answer yet. I will do that when I'm finished with the problem. And so it doesn't ask for a wavelength in meters. So to complete the problem, we need to do one more step. We need to convert the meters to millimeters, which is what it asks for. And so again, you should be able to recall this metric conversion. There are 1,000 millimeters for every meter. And so you should end up with a value of about 17.65. And if you round it to 2 significant digits, you would have 18 millimeters would be the wavelength of this radio wave. One more example that uses energy and wavelength. Let's say my green laser pointer, the one I typically use in class, has a wavelength of 415 nanometers. What is the energy of the light that is emitted from that wavelength? So you have your list of equations that could possibly be used here. You just have to select the right one and apply the correct units. We have wavelength and we want energy. And so the equation that relates those properties is this third one here. Energy is equal to Planck's constant times the speed of light divided by the wavelength. And so one mistake that will be common for many people is they'll just take the equation and plug in the values. And hopefully, if you're keeping track of your units, you'll recognize that setting the problem up this way is in fact a mistake. You'll notice that your meters would not cancel out because they are different orders of magnitude. And so this would give you the wrong answer. And so you have to remember that in order to use these equations, you have to express the units properly. And the units for wavelength have to be put into meters. So the first thing you need to do is a metric conversion from nanometers to meters. And 415 nanometers is the same as 4.15 times 10 to the negative 7 meters. And so now we plug in the values correctly, and you can see how the units are going to cancel out. And you should also think about the units you want to be left with. We're looking for the amount of energy, and the unit for energy is going to be expressed in joules. So the meters and the seconds better cancel out. You can see here that those seconds will cancel out, these meters will cancel out, and then you're left with a value that is expressed in joules. 4.79 times 10 to the negative 19 joules is the amount of energy associated with the green light in the laser pointer. So how are these light measurements useful to us? Measurements of light, or electromagnetic radiation, is the basis for pretty much every analytical instrument that is out there. You're measuring light, or you're measuring the way that light interacts with matter. And spectroscopy is the generic term for the measurement of light and the interactions with matter. And spectroscopy is all of the instruments that we use. We sort of classify them as spectroscopy. A couple of examples of spectroscopy or the applications, one would be an MRI machine, magnetic resonance imaging spectroscopy. And so that is used in the health field which uses radio waves to create an image representing all of the hydrogen atoms in a person's body. If you're unfamiliar with how many hydrogen atoms are in your body, pretty much every biomolecule that you're made of contains hydrogen. So your proteins, your amino acids, your sugars, your fats, all of those have hydrogen in them. And so it's useful to have an instrument that can make a picture of all of your hydrogen atoms, and it can give you an idea of certain regions of the body and what's going on there. Another application of spectroscopy is measuring global chlorophyll concentrations. Before the development of advanced spectroscopy, the way chlorophyll was measured in water samples was to take a boat out, take a water sample, bring it back to the lab, and measure the concentration. And so to get an idea of the global chlorophyll concentrations, that would take a long time. But now, since we understand the way that light reacts with chlorophyll or interacts with chlorophyll, we know that it absorbs red light and blue light at specific wavelengths and reflects green light. So we can use satellite measurements. We can send a wave signal, a light signal out of specific wavelengths and get an idea of the global chlorophyll concentrations immediately. And so we can get these updates nearly every day, which has really helped to advance the field. In order to build good instruments, we have to understand how light and matter interact with one another. And there are several different ways, predictable ways, that they interact. We have refraction, dispersion, diffraction, and interference. And so when light passes through matter, we know that the properties of the wave can change. The speed can change, the direction can change. And so understanding how they change is really important to developing more advanced scientific instruments. And so refraction describes when light passes through matter, the speed changes and the path will bend. And the most common example of this, or the picture that's used in most textbooks, is that picture of a glass of water where there's a straw in it, and it almost looks like the straw has been cut in half. But that's due to refraction, not that the actual straw has changed. Dispersion is when light passes through matter and it breaks up into its component colors. And so a prism is the perfect example of dispersion. And so if you need to isolate a specific wavelength, you can use a piece of matter that is going to disperse that light. And we definitely take advantage of that in our instruments. Diffraction is when light strikes an edge of an object and bends around it. If you think about it, you don't have to be looking directly at a light source in order to be able to see it. If you're sitting in a dark room and there's a light on in the adjacent room, you don't have to actually see the light to see the light coming into the dark room. The light is going to bend around the wall so that you can see it, and that's diffraction. The last type we'll talk about is interference. That's when electromagnetic waves interact with each other, and those light waves can interact in multiple ways. They can be constructive interference or destructive interference. If the wave amplitudes are in sync with one another, the wave amplitudes will add together, and that's going to make the light brighter. And so that's one way that we can increase the signal of a light. If you look at more modern flashlights, you'll see that they're usually made up of a bunch of different LED lights, and that's what's going to make the light a lot brighter. There's multiple lights with the same wavelengths, and those amplitudes add together to increase the brightness. A really cool phenomenon is destructive interference, where the wave amplitudes are equal and opposite to one another. And so you can see here that the wave amplitudes are in sync, but they're the opposite direction. And so they actually will cancel each other out, which makes it dark. So you have two different types of light making a dark region. This has been especially helpful in the development of ultraviolet visible spectrometers. And so when you're working in the lab and you're trying to measure the amount of light in your sample, you also have to consider the light in the room. And the light in the room can interfere with the light in your sample. But they've come up with ways to cancel out the light from the room so that you don't have to do all of your experiments in the dark. One specific type of spectroscopy is spectrophotometry, which is a quantitative measurement of the reflection or the transmission of light through matter. We often use solutions for this purpose, certainly not beer, but Beer-Lambert law is what dictates spectrophotometry. You may have already done this experiment in lab where you use the little spectrophotometers to measure the amount of chlorine in pool water samples. And so essentially what happens is you have a light source, and then you have this diffraction instrument that's going to focus the light, and the light is going to pass through the sample, and the amount of light that goes through will be measured. The amount of light that does not go through the sample is referred to as the absorbance. And with spectrophotometry and Beer-Lambert's law, the absorbance is directly related to the concentration of the analyte in the sample. You won't actually have to use this equation, but you can see that there is a direct relationship between absorbance and the concentration of the sample. So this is a quantitative way that we can look at how much of a certain analyte or a chemical that we are interested in measuring is in a sample. Next, we're going to talk about atomic emission spectra and how they led to the discovery of some of the modern quantum mechanic principles that we still abide by today. So we're going to have to take a little bit of a journey through classic quantum mechanics first. And so Atomic emission spectra were discovered, and light emitted from different elements produced a characteristic spectrum. So the spectrum is represented by these bands of light here that you see, these colored bands. And they were able to identify elements using those characteristic bands. And so Niels Bohr of Denmark, he wanted to explain why those line emission spectra occur. Yes, we've observed that they do occur, but what is causing them to create those different colors? And so some of the things that he discovered with his work include the fact that hydrogen has only certain energy levels, and those were called stationary states. Essentially, the electrons were put into specific energy levels around the nucleus. That is in fact still true today. One thing that's a little bit confusing about the way it was originally described is electrons don't exactly have an orbit in the way that you would think of a planet orbiting the sun. It does not have a circular pattern around the nucleus, but it does reside in a specific region around the nucleus that corresponds to its distance. And so when the atom is in one of its stationary states or the ground states, it's not going to radiate any energy. It's not going to be absorbing energy, it's not going to be emitting energy. But the atom can have the electron move from one orbit energy level to the other by either absorbing energy or emitting energy in the form of a photon. And so quantum numbers are used to describe how far away the electron is from the nucleus. And so the quantum number, lowercase n, is associated with the radius of the energy level. A low value for n means a small radius or a low energy level, and those are the ones that are closest to the nucleus. A high value for n means it's a larger radius and a higher energy level, and it's farther from the nucleus. And so electrons are in the ground state when they're in their lowest possible energy levels. So they're trying to get as close to the nucleus as they possibly can because they're attracted to that positive nucleus. When you have an electron moving into any other energy level besides the ground state, any higher energy level, I should say, than the ground state, we call that the excited state. So an atom can be in an excited state when one or more of its electrons is in a higher energy level than the ground states. Again, it requires an input of energy to be in the excited state. That's why they call it the excited state. And so when you have an atom, let's say one of the electrons in the atom, the ground state is in the first energy level, so quantum number n, 1. Let's say that electron is in the ground state. If you want to move it into an excited state, the atom would have to absorb energy, so that corresponds to absorption. If it absorbs enough energy, the electron gets promoted into the excited state, but it cannot stay there forever unless there is a constant input of energy. Typically there is not, so what happens is the electron will eventually relax back down, or it will emit energy in order for the electron to return to its ground state. So absorption is when you go from a lower energy level to a higher energy level. And emission is the opposite process when you go from a higher energy level back to a lower energy level. And one common application that's used, that absorption and emission is used for, that you've probably experienced, is in glow sticks. And so the way glow sticks works, most of you probably know you have to break the glow stick. Well, there's usually a glass capsule inside that contains often hydrogen peroxide because it's a good source of chemical energy. And then there's some sort of organic compound in there that when it absorbs the energy through the chemical process, the electrons go into the excited state. So they absorb energy, the electrons are in the excited state, and as those electrons relax back down, they emit photons, or they emit energy, and the wavelength of those waves correspond to different colors. So all of these colors that you see, you can find at the specific wavelengths that correspond to the visible part of the spectrum. And as you know, glow sticks don't last forever. Once you lose that constant supply of energy, the chemical energy that was provided, when the chemical reaction stops, eventually those don't glow anymore. And that's because you can no longer promote those electrons into the excited state and have them emit energy back down. And so what Bohr was able to achieve by looking at atomic emission spectra and coming up with the principles that he had discovered is that he was able to correlate the movement of electrons from excited state to the ground state with the colored bands on the hydrogen spectrum. For instance, this red band right here corresponds to an electron that moves from energy level 3 to energy level 2, and it emits a wave that corresponds to red light. The darker band here, this greenish color band, I know it doesn't quite correspond to this color, but it corresponds to electrons that are moving from n equals 4, so energy level 4, all the way down to energy level 2. And then here are the other two bands that are represented in the hydrogen atom. And so he was able to correlate those to the electron structure of a hydrogen atom, which was really important discovery at that time. And so the major limitation of Bohr's model is that it only successfully explains the atomic emission spectrum for a hydrogen atom. He was not able to successfully explain any other atom. However, some of the concepts Bohr discovered still apply universally. The energy of an atom exists in discrete energy levels, which we call n, and those correspond to the distance the electrons are from the nucleus. Electrons have ground states. They can absorb energy to move electrons from the ground state to a higher energy level, which is an excited state. And when those excited electrons move back down or move down energy levels, they emit energy. Two other gentlemen that contributed to modern quantum theory would be Einstein, I'm sure you've heard of him, and de Broglie. And they explored the concepts of wave-particle duality. Remember, originally people thought that matter traveled as particles, and that was separate from how energy behaved. And what they discovered was that matter and energy are just alternate forms of the same entity, and mass is the biggest property that distinguishes them. And so Einstein has his energy equation, E equals mc squared, so energy is equal to mass times the speed of light squared. And so all matter exhibits properties of both particles and waves. And then de Broglie thought electrons have wave-like motion and therefore only have certain allowable frequencies and energies. And if particles or if energy can behave as particles, like Einstein suggested, perhaps matter also has properties of waves. And so Einstein's equation was combined with this other energy equation that we talked about earlier in the chapter, where energy is equal to Planck's constant times the speed of light divided by the wavelength. If you put these two together and simplify it, you get the equation wavelength is equal to Planck's constant divided by mass times the speed of light. However, we know that matter is not going to travel at the speed of light, so they replace the c with u, and u is just a generic speed. It's not the specific speed of light. And so de Broglie discovered that matter behaves as though it moves in a wave, and that wavelength is going to be dependent on the mass of the substance. And he showed that the wavelength is inversely proportional to the mass, meaning the larger the mass is, the shorter the wavelength is going to be. And so for something very small in size, or something with a very small mass, such as an electron, this would be a very small mass, 9 times 10 to the negative 28. It has a relatively large wavelength, something on the order of angstroms. I know you don't normally think of that as a large number, but when you compare it to more massive objects such as the baseball or the Earth, you can see that these wavelengths are much, much smaller than those of the electron, and the mass of these substances is much greater. And so that demonstrates the relationship between the mass and the wavelength of particles. And so modern quantum theory, we came from classic quantum theory where matter is a particle and has a discrete mass, and energy is continuous and wave-like, and those were two separate concepts. But there were several discoveries by the gentleman we've talked about to lead us to modern quantum theory, which we still accept today, that energy and matter are particles, they have mass, and they can behave like waves. There are a couple of other people we'll talk about, one being Heisenberg, made popular by the hit TV show Breaking Bad. So we won't be talking about that Heisenberg, but the Heisenberg we are going to talk about, Werner Heisenberg, is the one who inspired Walter White's pseudonym. And so Heisenberg had an uncertainty principle, which states that it's impossible to know simultaneously the speed and position of a particle. You can either know one with certainty or the other. And so here is the Heisenberg uncertainty principle equation. You will not have to use this equation, but what you can see here is that we have the uncertainty of the position of the particle and the uncertainty of the speed of the particle. And so what we can get from this is that the more accurately we know the speed of a particle, the less accurately we know the position, and vice versa. And so the uncertainty is going to be insignificant for a massive object, but it's going to be incredibly important for something like electron configurations, which is what we'll study in Chapter 8. And those refer to where the electrons are in the atom. And so the joke I like to tell with the Heisenberg uncertainty principle is that Heisenberg gets pulled over by the cop. The cop walks up to his car and says, "Sir, do you know how fast you are going?" He says, "No, well, I know where I am, so there's no way I could know how fast I was going." Insert laugh track. Another principle we'll talk about is Schrödinger. And don't worry, you definitely won't have to know how to use this equation. If you move on to physical chemistry eventually in your chemistry career, you will have to solve that equation, and it is as bad as it looks. But the quantum mechanical model about the electron's position, we know from Heisenberg uncertainty principle that we can only know the electron's position with a certain probability, meaning we don't know for certain where it is. And Schrödinger came up with a very complex equation to describe the most likely position of electrons around the nucleus. And each of the solutions to the equation is going to give us an energy state or an orbital, if you know about atomic orbitals already, associated with the electron's position, and that represents the probability of finding an electron in a certain location. And so the most important part of Schrödinger's principle is that the probability of finding an electron is highest the closer you are to the nucleus. And so that refers to the probability density, the probability that an electron is within a certain volume. It's going to be more likely to be in this area close to the nucleus than it is to be in this area that's really far from the nucleus of an atom. Atomic orbitals are areas around the nucleus of an atom where you're likely to find electrons. Each of these orbitals can hold a maximum of 2 electrons. There are 2 different ways of visualizing atomic orbitals. We have the classic shell model, which is technically inaccurate because it makes it look like the electrons are orbiting the nucleus of an atom, sort of like planets orbit the sun, which isn't technically the case. But we still sometimes use this classic shell model because it's easy to visualize how many electrons are in each of the energy levels. For instance, there are 2 electrons in energy level 1, 8 in energy level 2, and 1 in energy level 3 for a sodium atom. However, we use a more accurate model, the quantum mechanical model, shown here on the right, which is accurate, but it's difficult to visualize exactly where these electrons are. And the quantum mechanical model was founded based on Schrödinger's equation, and each of the electrons will reside in these orbitals based on certain probabilities. Atomic orbitals are home sweet home for electrons. That's where you're going to find the electrons in an atom. And so all atoms, besides hydrogen, have more than 1 electron in them. And so we have to figure out where those electrons are going to be. All electrons have a negative charge associated with them. The nucleus of an atom has a positive charge associated with them. So each electron is going to repel each other, but are going to be attracted to the nucleus due to the electrostatic effects, meaning like charges repel, different charges will attract each other. So essentially what the electrons are trying to do, they're all fighting to get as close to the nucleus as they possibly can, but as far away from each other as they can. And so where does the atom put all of the electrons around the nucleus when it's got more than 1? Into these orbitals, which are regions around the nucleus in the electron cloud where the electrons are most likely to be found. And so it's like a little cloud of probability. There are 4 different orbital types that we'll talk about throughout the chapter that are labeled with a letter. So s orbitals, p orbitals, d orbitals, and f orbitals. And each of those has a different shape associated with them. And so we have quantum numbers to describe where the orbitals are, and we also use those to describe the electron's location. It's sort of like map coordinates, or I like to think of it as describing your seat location when you buy a ticket in a stadium, either for a concert or a sporting event. So on your ticket, it usually has a section number, it has a row number, and a seat number. Well, electrons have sort of a similar thing. They have a level, so that's sort of like your section number. There's a sublevel, that's sort of like the row number that you're in, and then the actual orbital location, which is which exact seat that you're in. And so the level tells you how far you are from the nucleus. The sublevel is the type of orbital you're in, those s, p, d, or f orbitals. G sublevels do not yet exist, but they expect that they might if they discover a new row on the periodic table. And then atomic orbital, that's the exact seat location. And so an s sublevel has 1 orbital in it, a p sublevel has 3 orbitals. So if you think of them like seats, if you were in a p row, there would be 3 possible seats that you could sit in. And inevitably somebody asks me what S, P, D, and F stands for. It's sharp, principal, diffuse, and fundamental. You definitely don't need to know that, but it always is a question that comes up. We'll talk about each of these quantum numbers individually. N, the principal quantum number, describes how far the electron is from the nucleus. And remember, this is based on Schrödinger's principle, where the probability of finding an electron is higher the closer you are to the nucleus. But as we know, there's only so much space around the nucleus. These electrons are trying to get as close to the nucleus as they can, but as far away from each other as they can. And so the electrons are going to organize themselves into discrete energy levels. So N of 1 will get filled up first, and then N2 will get filled next, N3, and then N4, and so on, depending on how many electrons you have. And so the possible values that N could be are integers between 1 and 7, assuming all electrons are in their ground state, which is all we're going to work with in this chapter. And these values 1 through 7 correspond to the number of periods on the periodic table. L is the angular momentum quantum number, and that describes the shape of the orbital. And so there are 4 possible shapes that we have, and we describe those shapes as either S, P, D, or F. And if you want to remember the types of shape, my SI leader Carlos came up with ways to remember them, where S corresponds to sphere. The S orbital has a spherical shape. P looks like a peanut. You have these 2 opposite direction orbitals. D is a double peanut. And then F, there's a lot of different types of shape, but they sort of go in all directions, so they sort of look like a flower. And so an S orbital corresponds to a value of L that is 0. For P, the value for L is 1. For D, the value for L is 2, and for F, it's 3. So S, P, D, F, 0, 1, 2, 3. Yes, you will need to know the numbers associated with the angular momentum quantum number. The magnetic quantum number describes the orientation of the orbitals. And so that is how many possible orientations you have will correspond to how many possible orbitals there are in each of the sublevels. And that's predictable based on the shape of the sublevel. And so with S orbitals, there's only one possible orientation, because if you take a sphere and you rotate it on an axis, you still have the same sphere. So there's only one possible orientation. And so every S sublevel contains one possible orbital. For P, you can have the P orbital be arranged around the x-axis, the y-axis, or the z-axis. And so there are 3 possible orientations for a P sublevel. And so every P sublevel has 3 orbitals available. For D sublevels, there are 5 possible orientations, and for S sublevels, there are 7 possible orientations. And some of you might be wondering about the weird-shaped ones here in the center, and those have to do with the way that you solve Schrödinger's equation. Again, you don't have to actually do that. And so the numbers that correspond to M sub L are these -3, -2, -1, and you will not need to be familiar with those specific numbers. The final quantum number that I haven't even brought up yet is the magnetic spin quantum number. And that describes the way the electron is spinning. Is it spinning clockwise or is it spinning counterclockwise within the orbital? I already mentioned that there are 2 electrons can be in one single orbital, and that leads us to the Pauli exclusion principle. Every electron in an atom is going to have a unique set of 4 quantum numbers. And so if you have 2 electrons in the same atomic orbital, that means that they have to have opposite spins. One of those will correspond to +1/2, the other will correspond to -1/2. And so a helium atom has 2 electrons in it. And the quantum numbers for these electrons, both of them will have n is equal to 1, meaning they're in the first energy level. They'll have an angular momentum quantum number, or L, of 0, meaning they're in an s orbital. They'll be in position number 0. Remember, you don't need to know these values. But electron number 1 will have a +1/2 spin, and electron number 2 will have a -1/2 spin. So here's a not-so-brief summary of the quantum numbers and the atomic orbitals that we have talked about. There are 4 different types of quantum numbers. You have your principal, angular momentum, magnetic, and magnetic spin. Principal corresponds to the energy level, and the possible values for those energy levels are 1 through 7. The angular momentum, or L, corresponds to your sublevel. Remember, those are your different shapes, S, P, D, or F. And the values that correspond to those sublevels are 0, 1, 2, and 3. The only two quantum numbers you're going to be responsible for in terms of understanding how to interpret the values are the principal quantum number and the angular momentum quantum number. But we also have the magnetic quantum number and the magnetic spin. And so the magnetic is the orientation, and the magnetic spin is the way it's spinning, clockwise or counterclockwise. And so let's apply some of these principles. What types of questions are you going to have to answer? Well, here's an ALEKS question where you're given the subshell, and what you need to do is fill in the principal quantum number n and the value for the angular momentum quantum number L. And so when you're looking at a subshell, it's a combination of a letter and a number. This number corresponds to the principal quantum number. So for a 6p subshell, n would be 6. And for the angular momentum quantum number, remember, S, P, D, and F all have values associated with them. A p sublevel corresponds to a value of L that is 1. And to remind you what those values are, S is 0, P is 1, D is 2, F is 3 in all cases. And so for a 6s subshell, the number, again, corresponds to n. So we'd have a value of 6. And then an F sublevel has a value of 3. For a 3s subshell, n would be 3, s would be 0. For a 4s sublevel, n is 4, s corresponds to 0. And for a 5d subshell, n is 5, and d is 2. And so you won't be given this little cheat sheet right here, but it's really easy to remember. SPDF 0, 1, 2, 3. We've talked about electrostatic effects throughout this chapter. Just to reiterate, opposite charges attract, like charges are going to repel each other. So electrons will repel each other, but they are attracted to the nucleus. And so electrostatic forces are the reasons why atoms have these multiple energy levels in these different locations around the nucleus where the electrons are put. And we care about where the electrons are because it has to do with how much energy the atom has, and it's going to help us to predict what types of reactions that these atoms are capable of undergoing. We know that the different energy levels are split into sublevels, and they go in order from lowest energy to highest energy. And the low energy corresponds to a high stability. So something with a low energy is very stable. Something with high energy is not very stable. And so we go in order S, P, D, and F. S has the lowest energy. F orbitals have the highest energy. And that's going to be important because it's easier to remove electrons from less stable energy states. So these high energy states, it's going to be easier to remove electrons from those energy states. So we can predict what order the electrons will be removed in. And so the high energy electrons are the ones that we expect to participate in reactions. And so what you're going to be able to do once we complete chapter 8 is predict the order of the orbitals that the electrons will fill around an atom. And that depends on how many electrons the atom actually has. And so the atom is going to fill the lowest energy orbitals first because those are the most stable. And the most stable orbital in any atom is the 1s orbital. Remember, 2 electrons can go into an orbital, so once we have 2 electrons in the 1s orbital, we move to the 2s orbital. And then a maximum of 2 more electrons can go into the 2s orbital. If you have more than 4 electrons, the next available energy level would be the 2p subshell. And so why is it important to know where the electrons are? Well, that can predict the reactivity. And to bring it back to something that you already know, you know that lithium is an element that likes to give away 1 electron to form an Li+ ion when it participates in ionic bonding. Well, why does lithium give away 1 electron? Well, if we look at the electrons in an atom, lithium has 3 electrons in its ground state. 2 of them are going to be in the 1s subshell. 1 of them will be in the 2s subshell. And we just learned that the 2s subshell is higher energy than the 1s. And so since there's 1 electron in that subshell, lithium likes to give that away to become more stable. Beryllium, let's go to the next element, we know likes to give away 2 electrons to form Be2+ when it participates in ionic bonding. And so if we look at the electron distribution, 2 of the electrons are in the 1s orbital, 2 of the electrons are in the 2s subshell, And the 2s subshell is higher energy. And so if it gives away these 2 electrons, it's going to be in a state of lower energy. So that is why beryllium prefers to give away 2 electrons. And so why do we care about where the electrons are? Again, it helps us to predict chemical reactions. If you're moving on to organic chemistry, the secret to organic chemistry, or being successful in it, is following the electrons. If you know where the electrons are most likely to be, you're able to predict what chemical reactions are happening. And so that is the end of chapter 7, and we will continue with these atomic orbitals in chapter 8 to electron configurations.